Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Chandra Krins. Chandra has been here a while ago as an intern. Actually, we were interns at the same time, so I know her from way back. She's now at the University of California at Santa Barbara, and for people who have gone there, it's like a beautiful place. So I'm extremely impressed by how productive she's been, despite the location. And so she's going to tell you about some of the work she's been doing on phase-aware profiling. Chandra?
Thanks much. Okay, so again, I'm at UC Santa Barbara. I'm an assistant professor there, and I run the laboratory for adaptive research on adaptive compilation environments, the RACE lab. And the work I'm talking to you about today is joint work with another professor there at UC Santa Barbara, Tim Sherwood, and my student, Priya Nagpurkar. So all of the work, or all the focus of the research that I do in the lab and all my students has a common theme, and that's adaptation. We want to be able to look at the way the program is behaving over time and how those changes occur, and also how the underlying resources are performing, what the CPU load is, what the network performance is, in order to try to adapt the program's execution to exploit these changes and try to extract performance. And our focus has been performance, primarily. The implementation of these ideas then usually come in the form of dynamic and adaptive compiler techniques and runtime techniques that are both resource and program aware. In order to do any of these things, of course, we have to understand or have a good feeling for what the underlying resource performance is or how the program is changing over time. That is, we have to be able to measure that somehow and make predictions from those measurements. So this requires something some sort of measurement, some sort of monitoring, in other words, profiling. And the profiling has to be very efficient because most of the time, we're doing it online. And so this is what I'm talking to you about today, one piece of our research, which is program profiling. But what's different or what's novel about it is that it's what's called phase-aware. So what I thought I'd do with this talk then is just give you background on what I mean by phases or phase behavior and phase awareness, because there's a lot of ambiguity in that term. I'll tell you how in the past people have been able to capture and characterize phase behavior in programs. I'll then talk a bit about a couple of tools that we've developed. First is a visualization toolkit. This will help me explain sort of phase behavior and let you get a feel for what it looks like as we're trying to do analysis on these programs. And that'll allow me to explain the remote profiling technique that we've implemented. And then I'll talk to you about some future directions and hopefully spur some of your interest on future directions, and then I'll conclude. So this graph shows a lot of different performance metrics for a particular program over time. What we're going for here is over the lifetime of a program, which is measured in billions of instructions, or is measured in instruction count. We have just a bunch of different metrics that you can get from hardware performance counters or through simulation. And the metrics themselves are things like level 2 cache misses, energy consumed, IPC, branch prediction misses, level 1 cache misses. And the metrics themselves aren't what's important here. What's important here is sort of the time-varying behavior of each of the measurements for each of these metrics. And if you notice, there's obviously trends. So we intuitively know that programs don't behave randomly, that there are patterns. And so the idea of phase behavior is to identify these trends or these patterns in the execution that go across metrics uniformly, and those are what we call phases. So in this graph here, what we're doing is we're breaking up the program into intervals, about 10 billion instructions per interval, and we're taking the average of the metric during that interval of time. We then can we can combine intervals, we can look at how similar two intervals are, and that combination then produces what is called phases. So in this program, we have 4 different phases that are occurring, and the way we come up with that is we just look at the similarity between these intervals, the profiles that we get from these intervals. What Tim Sherwood showed as part of his thesis at UC San Diego before he came to Santa Barbara was that you don't need to monitor all these low-level hardware-specific details. You can capture the same exact information in an architecture-independent way through basic block profiles. That is, you can capture basic block profiles for each of these intervals, compare these intervals, look at their similarity, and group the intervals into phases. These phases then directly reflect how the program is using the underlying hardware. Okay, so if you want to collect this information, you can do offline profiling. You can just collect basic block counts at certain intervals over time, and then you can compare these intervals. You can do it with online profiling, but obviously basic block profiles are very expensive, and so there's a lot of overhead introduced. So there's a lot of effort now to come up with sample-based online techniques that are either in hardware or software. Example software technique is a PC sampling. They're sampling the program counter. They're able to come up with a similar ability to capture phase behavior. In hardware, you could take these hardware performance monitors. It's now no longer architecture independent, but you could look for you could view them, this hardware performance data, as a time series, and then look for correlations and trends in the time series, of course. This has been done. What we use and what Tim has developed as part of his thesis is a special purpose piece of hardware. It sits on the chip, very low power, very low area, consumes a very small area. And it's able to collect, it's like a branch predictor almost, and it's able to collect this phase behavior for the individual intervals. But what's unique about it is it's able to make predictions for the next interval. So you're executing intervals, and the phase predictor says, okay, the next interval you're about to see is in phase 27. Okay, so that's really good. We're going to need any type of technique that measures phase behavior we could use for analysis. If we want to use it for online optimization, we have to have some sort of prediction. And so we're going to use this for our program profiling technique. And it has really high accuracy. Okay, so there's been some work on exploiting phase behavior, how to make use of phase behavior. The big ones are primarily, the only ones have been in hardware, and so I think there's a lot of room for doing some of the stuff in software. In hardware, there's been work on dynamic configuration of the processor, things like if you know that during a phase you don't use some of the functional units, next time you see that phase you can turn those off, save power, things like that. Tim used it to reduce hardware simulation time, and this is similar to the idea of how we're going to exploit it with profiling. The idea here is, if you're an architect or you're developing a new architectural feature, you can't just build it and test it. It's just way too expensive, way too time-consuming, so you're going to simulate it. But these simulations can take days, many hours, days, weeks, months, years, in some cases. So what SimPoint allows you to do is say, okay, I'm going to simulate an interval from each of the phases in a program, and then I'm going to record what the phases are that the other intervals are in. So you only need to simulate an interval in here, an interval in here, interval in here, and interval in here, and then you have a good picture of the entire execution of the program. So it significantly reduces your simulation time. So that's what's been done. And with our work, we want to, again, do it in software, do optimizations that it can exploit this information, these repeating patterns in execution. We built a tool set to help us get started. If you just collect basic block profiles, you have a huge amount of data. It's really hard to analyze or understand anything about it. And so we built a visualization tool that helps us filter this data out. And then we're going to use this information about the phase behavior to implement a new program profiling technique. And the technique is for programs that have been deployed to the user base, that have already been deployed. They're no longer in-house. And so what we're going to want to do is remotely monitor these programs to get feedback from how our users are using the program and hopefully then make use of that information. And we're focused on handheld devices, so it'll be resource constrained. Okay, so our visualization toolkit, pretty much just a set of filters implemented in scripts, Perl scripts. Any execution environment, again, this is not specific to managed runtimes or simulation environments or anything in particular. Any system that can generate basic block profiles can dump a trace in the format that we specify and use our tools. We've used it in JVMs. We're interested in using it as part of Phoenix. We've used it in simulation, and we're currently porting it to Paradigm, which is a parallel scientific computing, sort of high-performance computing analysis tool, instrumentation tool. Once you dump this information out, we have a bunch of tools that will help you get your head around what's happening in the performance of the program. One thing that's interesting I want to point out here is if you look at the intervals of the program's execution and you compare two of them, you have to have some sort of threshold for similarity. You have to say these two intervals they're not going to be exactly the same, so there's going to be some difference between them. How much difference can you tolerate? Turns out that the amount you can tolerate is dependent on what optimization you're doing or what you need to use this for. So we allow you, as part of our base classifier, to modify this threshold. If you make it a really low threshold, saying that any difference constitutes a new phase, then you have lots and lots of phases. You have a very high threshold, a lot of intervals will be grouped into the same phase, and you'll have fewer phases. So this allows you to do this and then to analyze the code within those phases to look for things like hot spots and what code's being executed and opportunities for optimization. So this tool, if you use it, outputs something like this, what's called the visualization part. It's a similarity matrix. It's just a bunch of pixels in grayscale. And our tool allows you to click on any pixel and it'll tell you what intervals you're looking at. What this is a matrix that compares every interval in the program to every other interval. So along both the X and the Y here, we have all the intervals from the start of the program to the end of the program. The top, we only show the upper triangle because the lower is exactly symmetric. So it's just confusing to look at. So we omit it. The way you look at this is that you start at a pixel, say the one in the top left corner there, and you proceed across the row. If you start here, this is the first interval in the program. You want to see how it compares to everything else. In our grayscale, we take the difference of the intervals, and we just take the Manhattan difference between the intervals. These are just vectors of basic block counts. And we compare them, and then we map them to the grayscale codes, the 64K colors, and we get colors, if they're more black, they're the same. If they're more white, they're completely different. And I just a very simple ray tracing, dual-threaded program. It's very simple, has 3 different phases. So a lot of black, a lot of white. How you read this is you start at the top right corner, and you proceed to the right, and you see immediately that you've never seen the phase before, so the first interval is going to be in its own phase. It's phase 1. Then you see a bunch of the same phase, a lot of black pixels there, proceeding across the row. And so they're all in the same phase. So all these intervals are exactly the same as all the intervals that came before it. When we hit this spot here, it's a white spot. It's that pixel says, well, this isn't a new phase because it's different from all the intervals that came before it. So we go down the column, and we say, okay, this is interval 14. We just count what interval we're at. And we're going to proceed across this row. What we find right away is that we hit a white pixel at interval 15. That white pixel, if we look above it in the column, we see what came before us. It's exactly the same phase as we were looking at. So what you see here on row 14, for interval 14, you have an alternating sequence between the first and the second phase. And then we get to phase 26, and this happens again. We reach this white space. We look before us and say, oh, nothing before us in time is the same. It's all white. So we go down to see what new phase we're in. Starts at interval 26, and that's going to be phase 3. Proceeding across the row of row 26, for interval 26, we just have an alternating pattern between phase 1 and phase 3. And then we have an alternating pattern between phase 1 and phase 2 and phase 3. Once we get down to interval 48, we're down here now. We are just in phase 2, and the last big chunk is just going to be phase 3. Okay, so that's sort of how you read these things. You just go across. These are just a couple benchmarks that we generated phase data for. The one on the left is a compression technique, compression decompression code. The idea here is you just take a big old buffer. It takes the first chunk of the buffer and it compresses it. Takes that result and it decompresses it. takes the next chunk of the buffer, compresses it. So you're alternating compression, decompression, compression, decompression. Very simple benchmark. It has exactly 2 phases, the compression code and the decompression code. So exactly what you see here. You have the compression code, you hit a section that's completely different, that's a decompression code. It hits a section that's completely different, you go up to the top of the row, it's compression. So you're alternating between two phases. Here's a database query processing. There's a couple of phases here. Again, some programs have a lot more phases. It just depends on the program behavior. There's a lot of stuff going on here. What's interesting here is that you have a lot of switching between phases in the beginning. And then you have a big old steady state. So you may want to focus in your energies here. Do your optimizations that you need so that when you get to this point, which accounts for over half of the execution time, you're able to, that's all specialized for how you're going to use it.
Is this interactive?
Yeah, well, it tells you what intervals you're looking at, and then you can use that information, the intervals, to extract all this information. What code's executing, exactly.
So, is it interactive in the sense that you can play around with how many different phases it detects? In other words, I'm curious. I've seen these figures before, and I'm curious about how much tweaking it takes to get.
Oh, no tweaking. You just put it on the command line and say, I want my threshold to be 90% instead of 80%, and you get a whole new visualization. You click on it, it'll tell you exactly what codes.
It does it quickly, basically?
Go very quickly.
Because I knew there was machine learning involved.
Oh, no, my stuff, this stuff doesn't actually group the intervals using machine learning. It actually just groups the intervals based on a threshold of Manhattan distance between 2 intervals. So, which is just the vector difference, really.
So the tool doesn't pick out the number of phases. It gives you this visualization.
Yes, and so you can, as part of this stat, it'll say there's 27 phases. Then you say, I want a threshold of 0.5. Oh, that's 0.5 would give you more phases, so there's 110 phases. And it gives you this picture. You click on it, and then you can get the code that's being executed there.
So what was the machine learning thing that was going on?
The idea behind that is if you had all the intervals, like I do, but I'm sort of looking at it incrementally. I want it online. The machine learning idea is that if you have all the intervals, what's the best way to put these things together? It's like a point in space. You're looking for like the centroid. You imagine these vectors as a point in a multidimensional space. You find a centroid, and then you see how similar these guys are to that centroid. Here, I'm just comparing every interval with every other interval, getting a value, which is the difference, and plotting that as grayscale.
Does it make much difference?
No. Absolutely not, and this is much faster.
Did anyone report that in a paper?
No, I haven't. I did this for Java stuff, and we reported it, but no.
I mean, there's people out there thinking that the right way.
Well, it depends on how you're going to use it. If it really matters that you get this right, that you group these things, that the differences, so that because I'm going to have some error, and I'm grouping things that aren't exactly similar,
right.
And they might not be the right exact groupings, but maybe having the right groupings benefits you in an optimization. I'm not sure. So maybe for something it would make sense, but it's a lot more work. Hugely computationally expensive. Okay, so now you want to exploit this information, okay, we sort of have a feel for this phase behavior that's occurring in these programs. And our idea is to use it for efficient profiling. And again, we want to profile codes that have been deployed to users. So due to time to market pressures, as we all know, we do ship code that's not fully optimized, or optimized for the ways that our users are going to use it, not fully tested. We don't know how the code's going to be exercised. These are complex systems. And so what we want to do is be able to, once the software is out there, to be able to sample the code as it executes and get feedback from our users about, in order to be able to do things like optimization, involve the software. If you know your users aren't using your full user interface, maybe you want to change your user interface. We want to do this dynamically. This is where we're going. We're also interested in seeing if we can't do this for bug isolation and program testing. We can do test coverage because we're getting real information, exact information about what the users are executing. Okay, so that's really nice and great and a nice dream. In order to do that, this has to be for users to participate, unless there's some major incentive, like a free Xbox. You need it to be very transparent. And so that means we can't be intrusive. We have to be very lightweight in terms of the computation speed. We don't want to slow down the programs. And we don't want to increase the communications that we're talking about these wireless mobile devices now. So very resource constrained. Big thing is battery power. any kind of communication we're doing, any kind of computation we're doing is we're draining the user's battery. They're not going to be happy with that. So this has to be very, very lightweight. So we have to be very clever about it. Okay, and our big vision is not to just sample a bunch of our beta users, is to sample all the time and to be able to partition the sampling across the user base. So not only do I want to sample a cell phone that is running my software on one of the users, I want to be able to just sample that a little bit and sample another person's cell phone a little bit and get a picture, the overall picture of how the program is being used and how I could optimize it for, or extract performance from it. So that's where we want to go. Of course, with very low overhead. Now this has been done for other uses, not for performance profiling. It's been used for bug isolation and program testing. Mary Jean Harold at Georgia Tech has done it for program testing, bug isolation. Trishul has some great work on this. Ben Livlett at Berkeley has really interesting work on this. Commonly, or what's a common theme in here when you're looking at program testing or Livlett's work on bug isolation is you're going to do random sampling. You're going to partition the sampling across your user base randomly or periodically. And so the actual sampling that's done is based on periodic or random placement. And they use different users. So first of all, we just want to focus on a single user. How can we make sure that the profiling is very efficient? That's what I'm talking about now. Here's our compress. We don't know that there's just two phases here. This is the execution time of the compressed program going across the row here. If you have a random or periodic sampling technique, you're going to take random or periodic samples. The problem with this is that random and periodic techniques do not consider this time-varying behavior, these patterns in the behavior of the program. They may miss things. Let's say your period is exactly the length of a decompress code that executes. So you're going to sample, just compress. You have a completely only 50% of your program's execution that you really are going to have good analysis data on. More importantly, though, there's a lot of redundant information being collected. If you're sampling, a certain interval, and you sample an interval that's similar to it, you're collecting the same amount of information multiple times. And so in a resource-constrained environment, this is not going to be tolerable. Any kind of unnecessary work should be avoided. So our idea then is use phase behavior, phase prediction, in order to do our profiling. Consider time-varying behavior and only sample according to what phases you've seen. For compress, we need to sample we need to sample a interval in the compress phase, and we need to sample a interval in the decompress phase. So much less overhead. We get the same amount of information, which I'll show you some of the data. But we sample much less. So the amount we're communicating is much less. We still have to communicate the fact that we're seeing the repetitions in the phase behavior, so we know how often these phases occur. And so we're just going to communicate phase IDs. If phase 27 is already executed, I'm just going to communicate phase 27, not the entire profile for the interval for that second time we see phase 27.
Question?
Yeah.
So is this presume a train and test phase where?
No, this is using this piece of hardware that is able to accurately predict what phase the next interval will be in. So it's online with hardware support and no training. So this is the sort of the architecture of our implementation. We have the phase tracker. This is all done in prior work and part of Tim's thesis. The idea is it's just going to look at branch instructions. It's going to collect information about that and produce what he calls is a fingerprint. And then it's going to keep track of a small history of fingerprints in hardware. It's going to use the history-based predictor to make an estimate of what phase the next interval will be in. It's very low power and it's a very small area. In the software, what we're doing is we're turning on and off profiling. When the phase predictor says, okay, here's phase 28, we've never seen phase 28, so we need to sample that interval. When that interval is done, we stop sampling, and we turn off profiling, and we proceed without. Yeah.
So, you talked about sort of changing the threshold and getting different numbers of phases. So how does hardware do that? What is it doing to do?
Yeah, it has a similar thing. It's using Manhattan distance pretty much. So it's part of the fingerprint. There's an entry for each branch pretty much that has executed. And there's, of course, some overlap there, but and it uses that information about the number of instructions per branch entry and differences that over time, and it makes a prediction on the differences.
How does it know how many phases it's trying to find?
Oh, it doesn't. It's just saying whether I've seen it before or not. It does not make an assumption that it's going to find 20 phases. There's just some threshold value that it uses. It's sort of like what I was doing with the visualization tool.
But it seems like with the visualization tool, it's interactive, so you can sort of say, well, that doesn't look like,
Right.
I guess that's my point. With the interaction, there's a human involved, right? That interprets what's being seen, and then there's feedback, right?
Right.
With the hardware, how would that work?
It's just that it's just empirical that you can identify a threshold that works for certain types of programs or some subset of programs.
What is the interval size? How do you know that?
The area on the chip.
Size of the interval.
Oh, the size. That's you dictate that. You have to choose that.
That's a hard fixed.
That's a parameter also. I mean, so yeah, you can. So
in the hardware-based scheme, is it a fixed value?
It's fixed value. It has to be fixed because that's how you're comparing over total size. You're comparing two intervals and they have to be the same size in order to see their differences.
Is there a particular value that works well for?
10 billion instructions. 10 billion. And the threshold of 0.8 is what we've been using. But you're right. I mean, that's why the visualization tool is important, I think, is that we have to understand what the impact of these parameters are. Tim has shown for lots and lots of programs that those are reasonable values. Again, it depends on what you're using it for. I can change that. If I only need very coarse information, I only need to know information about the two primary phases in a program, you can modify that. And so it'd be sort of like a hardware performance counter where you'd set a certain register, and then the hardware the phase tracker would use that as the parameter. Yeah.
So there's a trade-off here, right? So you're using this mechanism to do more intelligent selection of when to sample.
That's right.
And so like random and periodic has this redundancy you're getting rid of.
Right.
But to enable that, you're like, in some sense, tracing. The hardware, in some sense, is tracing certain parameters of the execution all the time.
Yeah.
So what's the, power overhead?
It's very low. It's I have it written up. It's in the very like 0.01 picojoules. It's per branch. It turns out to be. We have all the analysis for this, and that's turns out to be in the noise compared to the amount of power we're draining for communication and computation.
Because if you presumably have a program that's pretty random, like a lot of phases,
right,
then in some sense you might be.
This is a great point.
Expensive.
Right. So you may have lower accuracy, okay, because there's error in the prediction. I guess it's unclear as to if you just randomly sample, you're still going to have to cover more of the code in order to get the same amount of accuracy. So yeah, there's definitely trade-offs here. This is not the be-all end-all. This is an initial step in that direction. So to evaluate this, we did it all in simulation. We used an extension to Simple Scalar for the strong arm processor. We implemented the phase tracker for that, and we assume at 100% accuracy. Tim has shown recently that the accuracy is in the 95 to 98% range, but that's what we're working on now, is trying to see how that impacts our results. So what we're showing you is the upper bound on how well our phase profiling can do. Benchmarks, 6 different benchmarks, 3 pairs of encoders, decoders from the media benchmark suite. The initial data I'll show you is just on basic block frequencies. So when it tells us to profile, we sample the basic block frequencies. We're actually doing basic block counts initially. Then we've compared the performance overheads, computation and communication in terms of performance as well as execution time and power, and versus the accuracy. And we compare it against random and periodic sampling for different sampling frequencies. So this is the first set of results. What we have is across the x-axis is the percentage of the program that we have to sample. It's phase-aware techniques, an average random technique, the maximum random technique, and a periodic technique. The percentage of the program sampled, if you're doing a periodic technique, you just vary the period so that you're sampling more or less. If you're doing a random technique, you've got to know sort of how many intervals are going to be total in the program, and you're going to randomly select those. So we do that. And then for the phase awareness, we vary the the threshold of that similarity value. Notice if you increase it, that means that if there's, if two intervals are slightly different, they're going to be grouped in the same phase, you're going to have fewer phases. Sample less. Okay? If you make that threshold really low, two small differences will constitute whole new phases. You have more phases, you'll sample more. So that's how we vary it across. And so what we're showing here is the error in block counts. We take a complete profile of basic block counts, and we compare that exhaustive profile with what our samples produce. And so we do it in terms of percentage error. What this is showing you is that right about, around 4%, if you sample 4% of the program, phase-aware profiling is able to give you about 5% error. If you want to get 5% error for, say, a periodic approach, you need something like 18% of the program to be sampled. A lot more program has to be sampled in order to get the accuracy of the phase-aware profiling. And random never gets there. You can't even get down to 5% error. Okay, so I'm going to show more implications of this.
But how does error in basic block counts compare to error in phase prediction and phase accuracy? That's in some sense what you mean.
Right, I'm assuming 100% phase accuracy.
Okay.
I don't have numbers that show how the error in block count changes when you increase that accuracy of the. We have to just run numbers on that. Okay, now let's say you just want to sample 5% of the program, no more. You sample 5% of the program. This is just a different way of looking at it. I just wanted you to see how the performance varies over benchmarks. 5% of the program is being sampled. This is the error in block count again, percentage error in block count. And these are the different benchmarks. In all cases, phase profiling does very well, and MPEG is a little bit higher. What's interesting, though, is that periodic does well for all of the benchmarks except for JPEG encode. Is this right? I want to get this right. No, I'm sorry. The average random is doing best for all benchmarks, except for JPEG encode, where the periodic does better. So the point I want to make here is that regardless, there's not one technique that does best, except for in the phase case. If you use periodic approach for some benchmarks, it's going to work well, capturing the information. A random approach is going to work well in other cases. But in all cases, the phase-based profiling is able to accurately collect this information.
Periodic seems better than random.
Did I get that wrong? Yeah, periodic's worse. See, here's random and periodic. This is average random and periodic, so we're comparing these two. Random's better, random's worse. I just wanted to point that out. Sorry if I confused that. We just ran a bunch of different random runs, a ton, just regenerating the random numbers, just so we could, and then taking the average over all that. And then max is the worst you could possibly do if you really just had bad luck. Okay, so your question should be to me, who cares about basic block counts? Most optimizations we do today rely on profiles that are at much higher level. We're interested in hot blocks. Right? We want to optimize for hot blocks. We're going to group hot blocks together and throw out the cold blocks. We want to find hot methods so we know where to put our optimization energy for dynamically compiling. We don't care about anything else. So do we really need this level of accuracy in hot blocks is the question. Hot call pairs, we want to figure out where our inlining opportunities are. So we looked at all kinds of different profile types. I know there's a lot of data on this graph. All I wanted to point out is that the trend, the use of phase-based profiling, is able to capture accurately hot blocks, hot profiles, hot call pairs. I don't have data on it, but we're doing hot paths, and it all is able to capture this data with much less overhead, much less of the percentage of the program being sampled over the other techniques. Yeah.
So I would say that even this level is not enough, right? You want the next level where, it's ultimately the optimization. What's the performance benefit of getting, 95% accuracy in hot blocks? Maybe it doesn't matter.
Right. Well, I can tell you for hot methods, and this is just for Java programs. These are the top 10% of the hottest methods. If you're able to identify those accurately, you can get improvements of up to 25%. Okay, and the other optimizations I haven't done. The splitting out of hot and cold blocks, I think is a good one, right?
My question is if you instead of getting the top 10%, you get the top 9%.
Right.
You know,
Well, we've looked at all of this.
Is it like from 25 to like 15, or is it 25 to 24? Right? What's the gradation and the performance improvement by marginal inaccuracies in, you know, the profile?
That's a really good point. I don't have that number. We have all that data. We did all kinds of variations of this, but that's a really good point. I should actually look that up, compute that. Thanks.
So I'm curious about the non-monotonicity of the accuracy of the percent error.
Yeah, it's for the phase-based stuff, right? The problem is it actually turns out to be kind of an interesting effect. It's because when you start to modify the similarity between intervals, okay, so how we're changing percentage samples is we say, okay, if there's a little bit more of a difference between these two intervals, we'll group them together. Okay, because the intervals are 10 billion instructions, by grouping an additional one in, you can throw off how accurate the profile is. And I'm going to talk about this a little bit more in a little bit later, but it really depends on what interval you choose as your representative of the phase. Okay, so you have one representative, let's say it's the beginning. Oh, let me get to that. I'll get to that, okay? So it's a combination of those two. Sorry. Yeah.
So what benchmarks are used here? Because I would think that, you know, if the benchmarks are pretty regular phase behavior, like scientific benchmarks, this might work pretty well.
Yes.
But if you have some kind of random benchmarks like GCC, maybe it won't work as well.
Right. So GCC is really hairy, and it has lots of different phase behavior, and so you're going to end up sampling quite a bit. And so, yes, it's going to... the numbers are going to be... These are all encoding benchmarks. The one I'm going to show you in the next couple slides is GSM. I don't have individual pictures, but JPEG's really all over the place. It has lots of different phases. And if you look at that set of data for this block, it's JPEG encode that's really all over the place, and MPEG encode. So there's lots of different phases here. I should have the pictures for you, but I don't. GSM is much more regular, very few phases. Okay, so now, remember, our vision is to go to this multiple user, partitioning our profiling effort across multiple users. What's key here is the cross-input phase behavior. So say, you know, you're executing a program on your cell phone, and it executes phase number 27. I've recorded that. Our idea is to then communicate that you've seen phase 27 to, say, your cell phone, and say, don't sample this. Even if you've never seen it before, I've already got that information. I don't need it. So we can significantly reduce the number of phases we're sampling by communicating, by sharing this information. Now, of course, there's overhead in doing this. You know, there's lots of issues about communicating back and forth. But I just wanted to figure out if there's potential here. That means, is there phase behavior across inputs? And so that's the idea. And so this is GSM. Again, GSM is the most regular of our benchmarks. And it turns out that because you have to use the same size interval, 10 billion instructions, if you have a very short-running program, there's a lot that could be changing within an interval. And so what we found is that across inputs, it's only happens for some subset of benchmarks, like 25% of the codes that we looked at, we found cross-input phases. The problem is it's a problem of scale. And I'd love to talk more to people about this because I think it's a hard problem that I don't really understand it well. What I want to be able to do is say, this benchmark executed the exact same code, but at a scale that's different from this benchmark. Okay, and have those be enough to gather information about phase behavior. Right now, what I'm depending on is the exact same code executed in one input as it did it in the other, with the same frequencies, okay, the same basic block counts. And that doesn't happen all the time because it's usually input dependent. Okay, but for some benchmarks, it does work. And what I'm showing here is one that does work. This is GSM encode. This is 5 different, completely different inputs, way different sizes. And all I've done here is taken all the interval-based profiles from one input and concatenated it with the second input, third input, fourth input, fifth input, ran it through my visualization tool that compares all intervals with every other interval. So now I'm comparing intervals in one input with others from another input, and generate the phase behavior. Obviously, it's supposed to say black. There's only a few phases. If you look down deeper, if I had sampled all the phases in each of the different inputs, what I'd get is I'd have to sample about 27 different phases. If I'm able to communicate the fact that I have already seen these phases, I don't want to sample them again, you can cut it down by about 25% to something in the 17 range.
I think I missed something. So all of these phase IDs
synchronized across users.
Right.
Phase ID 2 may be different.
It won't be. If the hardware is the same, it'll be the same phase ID for the same program.
The IDs are computed dynamically too, right? As soon as the phase changes, you implement a...
Right, but if the phase IDs are really dependent on what code is executing, so what set of branches are executing. So the hardware is going to come up with the same phase identifier if the same code executes. And so that's going to be the same across the hardware. Now, I'm assuming homogeneous hardware. You can't have an x86 box in the front-end processor. So there's potential here. Not sure how often it's going to occur. If I can figure out the scaling problem, I think there's something there then.
I guess I'm confused about this diagram on the left. So if there's 5 inputs, wouldn't I expect to see 5 repeated patterns of phases? One for each input? Isn't time going right, left to right?
Oh, but it's time. It's like the first input, the second input, the third input.
Yeah.
And so we're just comparing the 2 intervals, and so the input, first input's about to here. It's going to be exactly the same as. The problem is that you can't see this very well because of this display. If you have our visualization tool, you can hone in. You can see actual differences. There's lines within this, and you can click on that. But they're all really similar. They're all still very similar. But given our similarity threshold, they're not exactly the same. So we're not considering them phases. If we change the similarity threshold, we can do much better. But again, it depends on how you're using this. But that's a good question. Okay, so I mentioned this a little bit earlier. This is our phase representative problem. What we're doing when we started out, just being naive, see an interval, and the hardware says, oh, this is a new interval, never seen this before, don't know what phase it's going to come from. We sample it, okay? But if you think about it, we have a lot of different intervals in a phase. Which one is the best to choose, okay? And the early phase work, what we were talking about before, when you're using these very advanced clustering methods, what you're trying to do is you're really finding the best representative of that phase. But we're doing this dynamically. We have to figure this out on the fly. We don't have all the phases. We don't want to sample everything and then decide, oh, this is the best guy, transfer him. This is the best guy, transfer him. We don't want to sample those guys. And so when we first were just naively sampling the first interval. If we did the centroid method, this is now, we sampled everything. We're going to try to find the best point in space. The best we could do in terms of error and block count is just about 8%. Randomly, we have all the phases, we've sampled everything, and we just randomly select one from each phase as our representative, and we take an average over a bunch of those. We get an error in the 17% range. Selecting the first phase, the first interval as your phase representative, gives us an error. It's almost 35%, which is just as bad as just random sampling. So when we first went at this, what we're finding is that the phase-based profiling is just as bad as random. But what's key is that you have steady state within these phases. If you think about it, you're executing a set of code, an interval. And it may have some code from the last interval that is similar to the last interval. It may have some code that's similar to the phase that's about to be executed. And so if you wait just a couple of intervals, we've looked at everything. We showed third here, the fifth, the seventh. And if you just wait till you're in the phase a little bit more, and then you make a sample, you can significantly reduce the overhead. So all those numbers I was showing you, what we're doing is we're waiting for the third interval to come along, and that's the one we're sampling. But it makes a huge difference, which I thought was kind of interesting.
So what happens if the phase ends before the third interval comes?
If you don't care. I mean, so this is going to impact if we're doing things like test coverage, if you want to capture infrequently executed code. So maybe we want to do something like the first phase. Different problem, though. So you're going to miss that. But if you're doing for performance, you want to miss that. That's not something that's going to occur frequently. Okay, so just to summarize the remote profiling, we have a piece of hardware, very small, very low area, very low power. It makes predictions about what phase the next interval is going to be. That's when we sample. After waiting until the third, it's important to wait until it's important to wait until the instability stops to get the best performance. We're able to reduce overhead by 50 to 75% over random and periodic approaches, just because we're reducing the communication and computation overhead of the profiling technique. And this is obviously it's going to consume a lot less battery power. I have actual numbers for that in a paper if you're interested in seeing those power numbers. We can also reduce this overhead further by partitioning the profile effort across users when there's similarity across inputs in terms of the phase behavior. And this does happen for some of our benchmarks, and so what we want to do is communicate the phase IDs to our users and say, don't sample these. Okay, so there's lots to do here. Okay, these are just initial results. Lots of actually exciting things, I think. The first thing to do, and one big thing you should be asking me, it's really nice to have our little hardware piece of phase hardware telling us when to sample. I'm just telling you, we're turning on profiling and sampling. Well, how do we do that? That turns out to be a very hard problem, especially when given restricted resources. We have to find clever ways to turn on and off profiling. So we have lots of ideas. I have a student that's working on this now. We're looking at hardware and software techniques. A big one in software is just to do code duplication. But in resource-constrained environments, this turns out to be really tough on the memory hierarchy performance, which drains the battery, as well as just on space. We just don't have that kind of space available to us. So what we're looking at is combining this with dynamic pre-compilation and code unloading to try to get the same kind of sampling benefit. We're also looking at interesting prefetching ideas to help improve the memory hierarchy performance. And then for the hardware side, we're looking at, I'm working with E. Lewis at University of Pennsylvania with his DICE system, which is a hardware-based dynamic expansion of instructions. And so you're executing a code, you hit an instruction. If you turn on profiling, you're going to execute, and that instruction is going to expand into profiling instructions plus that instruction. But later on, when you turn off profiling, that instruction doesn't expand and you just execute at high speed. So that's what we've been working on this summer with another student of mine, Hassan Mousa, is working on that. We have to be able to petition this across users. Again, I want to work on the scaling factor thing that I mentioned to you. A lot of the feedback I get is we don't want hardware-based techniques. It's really hard. How is Intel going to get this on the chip and deploy it on cell phones in the short term? That's going to be really hard. Tim's actually building this in hardware now. And so we will have a prototype in hardware to show that it is low area and low power. So maybe that'll help. But we want to find alternate approaches to doing this phase prediction online. We have a bunch of ideas. But first we have to figure out when we're doing prediction, what is this error impact? Both in the hardware, plus in software, you're going to want even more error because you're going to want it to be very lightweight. How does this error in prediction of what the next interval, what phase the next interval will be in, how does that impact the approach? And then I'm really interested in experimenting with how to make use of this for test coverage and bug isolation. If we invert the problem, instead of looking at the most frequently the similarity between intervals, maybe we could look at the differences between intervals to see sort of infrequently executed code, what's being executed when, what things are executed at the same time, and maybe it'll help us pinpoint where bugs are or help us develop better test cases. Okay, and then we have a bunch of adaptive optimization techniques, and this is completely separate. Given that we have phase behavior, or this ability to profile some phases, how can we take advantage of it in software? It's primarily our focus in this area has been on improving execution performance. And we're looking at lots of interesting domains, internet and mobile computing, of course, but also scientific computing, which I'm just going to mention here in a second. And again, for the mobile environments, we really want to reduce power consumption. That's our goal. So here's a couple of the ideas that we're going for. For internet computing codes and managed runtimes, we want to be able to use dynamic optimization to take advantage of repeating patterns in this phase behavior. We're looking at specializations where you specialize the computation for specific values, specific behaviors, different optimizations. One thing we're doing is scaling the voltage. If you have a phase where you're doing a lot of I/O and your processor is just sitting there idle, when that phase repeats itself, you can scale down the voltage for that phase to reduce power consumption for a battery-powered device. I'm interested in investigating code and data layout. I think that it's interesting. There's an interesting relationship between what code is executing and what the performance of the memory hierarchy is going to be. So how do we want to do that? And of course, we can just use garbage collection in these managed runtimes to help enable this. This is all exactly what Trishal's done. I just thought maybe it'd be interesting to see from a phase perspective if there's something there to improve performance. We've also looked at scientific applications, trying to do the same kind of thing, trying to improve the program over the life of the execution. What's interesting here, though, it's not dynamic compilation. All high-performance systems are not really focused on, don't really like the idea of dynamic compilation because it introduces overhead. And so we're interested in using a feedback-based static compiler where you specialize the code and then you dynamically switch between the pieces of specialized code dynamically. And what's really nice about scientific codes is similar to what we've seen before. When I was talking about for that cross-input thing, there's two key benefits to doing this for scientific codes. One, there's very few phases, so you can really focus your energy. These are really poor on the screen, I'm sorry to see. These are this linear algebra computations, just 2 phases. There's no I.O. in this benchmark. This is a benchmark that does actually 5 different things, a couple ray tracing algorithms, some molecular dynamics algorithm, and a search kernel, and you can't see it very well. There's 5 different phases, 1, 2, 3, 4, and then 5. And so it's really easy to kind of focus your energies on specializing these types of codes. The other thing that's really cool is the cross-input benefits that you get. In this last program here is a DNA homology search application called Pattern Hunter. There's some I.O. in the very beginning, way up here, and then a lot of I.O. at the end. And it has 2 primary phases. You can start to see some of the differences here. Depending on how you're optimizing, you may want to focus in on separating these out in terms of phases. But if you're just looking at sort of coarse-grained phases, this is plenty of information. Across inputs, there's a ton of similarity. Again, a lot of things are based on the size of the input, but for many of the programs that we're looking at, there's a lot of repeated phases. And so we're able to sort of exploit that fact. What's cool about that is that means that I can, for using feedback-based static compilation, that means I can profile 1 or 2 inputs and have a good picture of how most inputs will execute. Okay, in that computing code, that's not the case. There's lots of variation across inputs. And here, it turns out there's almost all the phases are repeating themselves across inputs. Okay, so my main point is really that there's phase behavior in programs, and this is perhaps just a different perspective to kind of look at performance optimization. Allows us as programmers and optimization developers to focus our energies. There's, again, a ton of ways to collect performance data. There's a ton of data. It's very hard to understand what it means, where you should focus your energies. And so the visualization toolkit really helps with this. I mean, we've really been able to identify where to spend our time. Then if you're using one way to use phase behavior is with this remote profiling idea, and that's the whole goal is just to reduce computation overhead, communication overhead, and power. There's lots of application domains as well as potential uses besides, again, this is not specific to managed runtimes. We can use it for scientific codes, we're hoping. We can do all kinds of cool stuff. Program optimization, specialization, remote debugging, and specialization. Remote sort of software upgrades is where we're hoping that phase behavior will help us. So that's really one of my projects. I just want to mention a couple others that in case you're interested in any of this, and I'd love to talk to you more about them. I have lots of really, really great students. Salim Goran, he's pretty much interested in resource-constrained environments, and he's looking at really SensorNet environments. And he's come up with a very lightweight statistical prediction system called the NWS Lite for resource-constrained devices that may not even have a floating point unit. And we've been able to achieve highly accurate predictions with very low computation overhead. And the goal of our work is to efficiently partition these large-scale applications across a sort of a sensor-based system. Because a lot of times you're going to collect a lot of data. Transmitting that data consumes a lot more energy than performing computation. So what we want to do is actually do more computation within the sensor net. And his techniques the goal of his techniques are then to partition the work efficiently so that we reduce the power consumption of the overall system. And these are all battery-powered sensors, is what I'm talking about. In terms of the CLR, managed runtime, I have a couple students working on this where we're just interested in trying to use the ideas for efficient mobility that we've had, both resource awareness and program awareness, to do optimization. We're also working with Michal Cherniak here at Microsoft on modularizing the VM with a special purpose language called LIL. And then lastly, we have all kinds of adaptive runtime techniques, things like adaptive garbage collectors that allow you to switch garbage collectors on the fly very, very, very efficiently. We have a paper on it at ISMM. If you're interested in that, it's pretty exciting. We really had a lot of fun with this project. continuing to work on it. We do adaptive compression, transparently intercept communications over the wireless, apply compression on the fly. The type of compression you use, the actual technique you use really matters. Some consume more resources than others. This is a resource-aware technique where we're looking at CPU load as well as network bandwidth transfer for the transfer to improve transfer performance. And then just online and offline profile-based optimization techniques. So that's all I have. I'll take questions if you have them, and send me an email anytime.
So have you had any experience looking at actually annotating the code directly? Sort of say this, the phase begins here, phase ends here.
Yes.
And how does that work?
Yeah, it's actually what we call them as phase signatures. And the problem is a phase consists of bunches of basic blocks, not necessarily from the same method. So it's really hard to, so the idea first was, well, maybe then we should reorganize the code and then apply these phase signatures, because what we found was we have to annotate lots of different places, and to the time, for a period of time, the path might be in one phase, and that path might be included in a different phase. And so capturing that time, where in time you are in the program, turns out to be quite hard. You see, so, it's not that if this code executes, it's already always in this phase. Lots of times it's in different phases, and it's just a different branch that's taken that throws you off into a different set of executed code, different body of executed.
So you're saying there's no unique path that would identify when you enter or exit a phase?
Well, we're looking at that right now. That's where we're going with this, because just doing it naively, no. There's no way without code reorganization that you can do this efficiently in terms of the number of annotations you need and trying to figure out where you are in time. So that's why we're doing hot path profiling, one, to see how accurate it is with phase-based profiling, but also to try to give us intuition behind when to apply phase-based optimizations without sampling the code dynamically. Yeah.
So what kind of data do you get from this? Like when you say you spend 20% of your time in a particular phase, how do I, as like a user who's trying to improve my program, know what that phase, is?
Right. That's fine.
Do I know what particular code is?
Yes, exactly. So that's what the tool tells you. So let's say you have a big black blob on your phase visualization output. You just click on it, click on the center of it, and it'll tell you what phase you're in. And that phase then, you can specify this, but you can say, I want the most frequently executed basic blocks, the most frequently executed instructions, the most frequently executed methods. And you can filter this out with various filters.
So it basically gives me a summary for that phase of what kind of code was running during that phase.
That's right.
Okay.
Yeah, it tells you you can do anything with it. It can tell you all the different methods that executed during that phase, all the most frequently ones. Basic block level. It'll actually give you the code. We have it linked to it. It's a JVM. But anything, if you're able to dump this phase behavior as well as a map to the executable, or some intermediate form, depends on what type of instrumentation tool you're using. It just all links together, and you can get instruction-specific data.
And does the accuracy of this vary, whether it's like multi-threaded or single-threaded? If you've got a bunch of different threads doing different things, does it kind of figure out that they're different threads or that they have common?
So this is a really good question. We've only really looked at, we've run some multi-threaded codes through it. That ray tracing one was one of them. This is a really interesting problem that we haven't really dove deeper in. You can collect this information at the thread level, and so then you could look at thread-based phase behavior. But right now we're at a much coarser grain. We're just saying program execution. But it just matters where you're collecting that information. If you can specify, if you can differentiate between threads, then you can do thread-based behavior. People who are doing this are actually using this visualization tool at SDST. They're interested in multi-threaded parallel codes and those that are multi-threaded, but they're doing the same kind of thing. They want to figure out on a per-thread basis where the thread's spending its time and sort of how threads then compare. And so that's what they say that they want to use the tool for. So this is a good area to investigate, I think.
This is kind of the inverse of that. His question was, in general, how often do the phases that you find in the sort of dynamic phases that you detect map to what, like, a logical phase would be in terms of the programmer's mind, in terms of, like, so we've got these phases, and we've got these profiles for them. You've got 4 phases in your program. Here's what they are. Would they, in general, map to the user's theory of what this program does and what phase?
Yeah, it depends how complicated the program is. For scientific codes, exactly. I mean, there's obvious. I could tell you ahead of time where the phases are going to be. But for some of these internet computing codes, any of the compilers, the Java GCC, the Java C, they're both all over the place, and no, you have no idea. And so then you start messing with your similarity thresholds to see how to start grouping these things, and maybe it'll give you some insight into how you should reorganize the code or what things you should do. That's what we've sort of been using for we're just running a simulator, and we're having trouble with the performance, and we've used this to analyze sort of where we're jumping. Why is there 50 million different phases, and and how can we start to reorganize our code? And so that's helped. Yeah.
In the context of the scientific applications, since so many of them are just using off-the-shelf libraries, have you found any advantage in trying, or someone considered doing some specific work and then analyzing the libraries in and of themselves, and then figuring a way to get some efficiency by taking what you learn about the behavior of those libraries, and when they're incorporated into larger programs where they obviously correlate pretty strongly to major phases, saying, here's some known behavior we don't have to regen, or we can use a starting point.
Right. Yeah, I think that's really good work. There's been some profile-guided work in this area. Brad Calder's done, right, for specializing libraries, but not phase-based. But again, it doesn't matter. It just matters what code's executing. So you could do exactly this, where you could just specialize like 2 or 3 different specializations of the most frequently executed paths to the libraries. Maybe, I don't think you need that many of them, actually, because it's usually common. If one piece of code executes, a lot of the remaining code in that interval is going to execute. It'd be a great way to sort of specialize your libraries. And I think you could do that for managed runtimes where you're using a lot of library code the exact same way. So that'd be a huge area to investigate. Other questions?
All right. That's fine.
Thanks.
How realistic is that you could actually profile more than one application at once? Is it?
Oh, not. It depends on your instrumentation tool. Paradigm's really nice, it turns out of University of Wisconsin. And I think that with that tool, I could do workload-based profiling. If I can do, and also, what other tool we were looking at? Again, you have to be able to separate out your profile data. And once you have that, then you have to change the visualization tools, but it wouldn't be that hard. But actually getting the information and have it be accurate might be a challenge.
Paradigm also introduces some space issues.
Hopefully that'll be good. Any other questions? Great. Thank you so much for coming.